A surface may have the correct dimensions, but the part still doesn't sit properly. The joint leaks, the surface rocks, and the bolts don't tighten evenly during assembly. Even when all dimensions are within tolerance, the system loses its function. So where is the problem? Not in the dimensions, but in the surface itself. Today, we'll look at the concept that defines this situation: flatness. Flatness is the condition in which an entire surface must lie between two parallel planes. The distance between these planes is defined as the tolerance value, T. No point on the surface may extend beyond these two boundaries. This defines the form of the surface, not its size. A part may be 10 mm thick, but if the surface is bent by 100 microns, the part is no longer functionally flat. Flatness is a form control, which is why it is always written without a datum. Flatness supports dimensional tolerance, but serves a different purpose. A dimensional tolerance limits the distance between two surfaces or points. Flatness limits the shape deviation within a single surface itself. A surface may measure 10 mm plus minus 50 microns. But if the waviness exceeds plus minus 20 microns, that surface will not sit properly. According to ASME Y14.5, the flatness value is generally kept less than half of the size tolerance. This makes manufacturing easier while keeping the surface form functional. Flatness ensures true contact between surfaces. A joint that doesn't leak, a sensor that aligns properly, or a plate that applies even pressure, all depend on this control. Especially for sealing faces or reference plates, flatness is a critical parameter. Functionally speaking, when form fails, contact is lost. When contact is lost, function ends. That's why flatness is the guarantee that form protects function. The flatness tolerance zone consists of two parallel planes. The actual surface must remain between them. It is expressed with a single symbol, a square containing the flatness mark and a tolerance value. This means that no point on the surface can extend outside those two planes. Like all form tolerances, flatness is not referenced to a datum. Because it controls its own surface, not relative to anything else. The goal in flatness measurement is to determine the difference between the highest and lowest points on the surface. In classical methods, the part is placed on a granite plate and scanned using a dial indicator. Modern CMMs collect a cloud of points and analyze the surface against mathematical planes. Optical systems, such as laser or structured light scanning, provide micron-level accuracy, especially for precision components. Whether contact or non-contact, the goal is always the same. Zmax, Zmin less than or equal to tolerance. Flatness brings clarity to both designer and manufacturer. The designer defines functional flatness. The manufacturer is free to decide how to achieve it. This avoids unnecessarily tight size tolerances, while still ensuring that the functional surface is guaranteed. For example, defining the ground surface with a flatness control improves both quality and cost efficiency. The rule is simple: define what is needed, not how to do it. Common mistakes when specifying flatness. First, confusing it with surface roughness. Surface roughness describes microscopic texture. Flatness describes macroscopic form. Second, adding unnecessary datums. Flatness is a surface control. It is not referenced to anything else. Third, using the wrong symbol in median plane situations. Median plane flatness is a special case. We'll explore it in a later lesson. An engineering team notices that a sealed cover is leaking during testing. All dimensions are within tolerance, but the surface is bowed by 80 microns. When a flatness control of 50 microns is added, the ground surface achieves 100% sealing. The dimensions didn't change, but the surface became functionally flat. That's the power of GD&T. It controls behavior, not just size. Flatness is the foundation of all form tolerances. Without understanding flatness, it's impossible to master shape, orientation, or profile controls. In the next lesson, we'll move to the linear version of flatness, straightness. Stay tuned, because the right tolerance always leads to the right result.